Hey, so today we're talking about something called the first derivative test, and basically it's using the first derivative function to gather information about the behavior of the graph in terms of its slope. So what does a derivative represent? Derivative represents the slope of the tangent line to a function or a curve. So for our purposes, whenever we hear the word derivative, we can just always picture slope, right? In terms of is the graph rising? Is it falling? Does it experience a slope zero? So we're going to use the sign of a derivative to help us visualize how the graph is moving. Is it rising? Is it falling? Is it experiencing a slope zero? So when a function is increasing, what's common about the derivatives? F prime is going to be positive. When the function is decreasing, what's common about the derivatives is that f prime is going to be negative or less than zero. Likewise, if f prime is greater than zero, then my function is going to be increasing or rising. And we always read the graph from left to right. So increasing means it's rising from left to right. Decreasing means from left to right, the graph is falling. Okay. When f prime is less than zero, f of x is decreasing. And when f prime is equal to zero, our function is constant, meaning that it's going to experience a horizontal slope, or it is potentially changing direction. So I feel like a lot of this process that we're going to take is going to feel familiar because you've already been doing it to some extent with your velocity sign line. Your velocity sign line finding where the object is at rest, and then testing each subinterval so that you know whether your particle is moving left or right. It's going to feel the exact same procedure. It's just that now it's more of a visual in terms of, oh, is the graph rising and falling instead of is the particle moving left or right. So I think you're going to find this very, you're going to feel like you've done this before in some respect. So example 1 says this: determine the intervals at which the function is increasing and decreasing. Locate the relative extrema. So just like how we would approach this problem, if I were to ask you, find when the particle is at rest, you would find velocity function, which is the first derivative, set equal to 0. Same process here. We're going to find critical points by setting f prime equal to 0. We want to first find out where slope is 0, and then decide what's the behavior around those critical points. So let's find f prime. A power rule can handle each of these terms. So we'll bring down the 3. Right? The linear goes to a constant, and the constant goes to 0. Okay, we set f prime equal to 0. Now we can factor and solve. Multiplies to be -6, adds up to be 5. Next up, we're going to create a slope sine line, much like how you would do your velocity sine line. Okay. And then you'll pick points in each of the subintervals. So I'm just always going to pick numbers as close to 0 as possible. Makes it easier for me to plug in. And we like factor forms. Factor forms helps us get to our sine a lot faster. So -7 will insert itself in for x. -7 plus 6 is negative. -7 minus 1 is negative. Two negatives make a positive. So I know that in this subinterval, my graph is going to be experiencing a positive slope. And I like to give a I like to use arrows to kind of give a visual as to how the graph is looking. So I like to use an arrow pointing up like that. That just gives me an indication that is how the graph is rising, or that's how the graph is behaving to the left of -6. Next up, my test point is 0. So 0 in for x, 0 plus 6 is positive, 0 minus 1 is negative, positive and negative is negative, so my graph is falling in that interval. Next up, I can test 2. 2 plus 6 is positive, 2 minus 1 is positive, so my graph is going to be experiencing a positive slope in that interval. Now, just like with velocity sine line, once we use our test point for the purpose of identifying the sign of that interval, these don't mean anything, right? So we don't want to write any of our interval statements involving those test points. Your interval statements is just going to involve around -6, 1, and potentially the infinities, but we're never going to involve the -7, the 0, or 2, except to fill out the behavior of the graph in that interval. So this tells us how the graph is rising and falling. What do you expect then at -6? Because the graph is falling followed by rising followed by falling. There must be a what at -6? A relative maximum, right? There's a hill of the graph. Hill of the graph we know is relative maximum. What do you expect at 1 then? Relative minimum, right? So it says locate relative extrema and write out intervals of increase and decrease. So this is the way that we can write it. We can write out all those statements. F of x is increasing. And when would the graph be increasing? Which interval would you say? And 1 to infinity, okay? You can use a union or comma, doesn't matter. Now, something that I'm going to be looking for on your assessments is looking for justification. So justification, you're going to say because f prime is greater than 0. Make sure that you name your graph. Okay, don't say graph or it. Name your graph. And that's something that they look for on the AP exams too. If you just say, oh, because the graph is greater than 0, or because the slope is greater than 0, name what be more specific. Okay? Don't say graph or it or slope. Okay, f of x is decreasing. We see the interval, negative interval here. So negative slope interval here from -6 to 1. And our justification is because f prime is less than 0. Okay, we can also say a statement about relative max and relative min, just like how you guys said. A relative max at -6, a relative min at 1. So we can say relative max now, let's say I wanted to ask you for the physical location of the relative max. Then what would you do with how would you find the full order pair? Original. Okay, so I'm going to show you what that value is. If I were to plug back into the original, I'll get 51. Okay, so and the reasoning is because f prime changes positive to negative. Depends. Sometimes I will ask you just for the x value. Sometimes I will ask you for the y value. If I ask you for the y value, you have to insert back into the original function. But if it's a messy value, then I'll have to give you a calculator. I won't make you do messy calculations without a calculator. Okay. We also have a relative minimum. This case, we do have a relative minimum because the graph does fall, followed by rising again. And if I wanted to find the relative minimum y value, it would go back into the original function. So I just want to show you where that number is coming from. It's coming from the original function. Change it from negative to positive. Okay, next page. Example 2. Determine the intervals of increase, decrease. If there's any relative extrema, find them as well. We know that all of our increase, decrease is going to come from f prime. But if I want to find f prime, I got to involve what? Quotient order. Okay, let's clean this up and see if we can find critical points that we can identify that we can place onto our slope or derivative sine line. Okay. Yeah, we talked about with quotient rule, do not try to do anything with the denominator. That denominator is perfectly fine where it is. Don't have to FOIL out. Okay, so there's my derivative function. I find critical points as same as in the past. Look for them in the numerator and denominator. Anything from the numerator? No. Anything from the denominator? X equals 3. Now, look at the original function. What's happening at x equals 3? Not a whole, but yeah, vertical asymptote. Yeah, there's vertical asymptote there. But so we know that there is no chance this could be a relative max or relative min. But we still want to place it onto our slope sign line, our derivative sign line, because it will help separate our intervals of increase, decrease. So critical point at 3. So we're going to place 3 onto our sign line, even though we know that it doesn't, even if there was a fall followed by a rising, we know this can't be a relative minimum. We already know there's a break on that graph. Okay, so we'll pick points on either side. Here I'll choose 0, and I'll choose 4. Okay, we put it into our derivative function. Test points. Numerator is negative 17. My denominator is always positive here because it's squared. So it doesn't matter what number I plug in. It's always a negative over a positive, which is negative. And if I plug 4 in, negative or a positive, same idea. So my graph is going to be falling or decreasing, and then there's a break, and then it's going to continue decreasing again. Now, typically I would say don't merge. This one, you definitely can't merge the two behaviors and say, oh, I'll just say from 0 to infinity, because there's an asymptote there. There are times when you can merge two behaviors together into one statement. But I would say, just to be safe, if you always separate your intervals of decrease and increase, you're never going to run into trouble. So I'm just always going to say, just always separate, even if there are times you're able to put together. That way you don't have to figure out, wait, should I merge or should I not? Just always separate, and that makes it an easier decision. Okay, so we can say our function is decreasing. On the interval from -infinity to 3, and then break 3 to infinity. Again, we don't want to use the 0, the 4, or any test point, right? Those are not going to show up anywhere except to help you fill out your signs. What's our justification? Because less than 0. Is there any other statement that we can make about increase or relative max or relative min? No, that's all we can say. This only behavior. Okay. Just to clarify here, no relative extrema.
You want us to write that if there's not one?
Yeah, I think on the quiz I'm gonna have like spaces for certain things. So if there isn't one, then you wouldn't just put anything there. We're gonna spend a specific day talking about derivative graphs. So we're gonna skip example 3. And the rest of the period, we're just going to do practice problems, okay, with first order tests, practicing writing out our because statements and our justification statements. So let's go to page 16. And we'll just try as many of these problems as we can. We'll start off with an easier one here. Start off with 21. So the direction says, find critical numbers, and then create your then you'll create your derivative sign line, and then populate that sign line. Then you can determine intervals of increase, decrease, and relative extrema. So once you find f prime, I would say take out your GCF first. Then it's easier for you to look for your critical points from there. Okay. You find your critical points here. At -2 and 1, populate your f prime sign line. And then let's practice writing out all of our statements, right? F of x is increasing. If you run out of room, use 19 to write out. We're not going to do 19, so if you run out of room, you can use that space to write your because statements. So we have everything here, right? We have increase, we have decrease, we have relative max, we have relative min.
So they misunderstood what you meant by exact value. They still have the answer, but they don't have it down here. So they integrate by earlier. So it's the right answer. It's just industrial.
Yeah, I don't know what to do with that yet. So just write out what is supposed to be. And then
But up here they have it written down.
that's fine. That's fine. Yeah, that's right. Okay, notice all of your because statements. Let me point something out here so you can just be aware. On assessments, on quizzes, on tests, students are good about these, but not so good about these. So I see students, they would leave those out because they feel like these don't require a because statement and these do. So typically, I see students losing points in these places because they don't put because statements for relative max or relative min. Be aware of that. And then these y values I found just by inserting back into the original function. We'll do 25 and 33. Okay, 25 and 33. 25 looks complicated. Because we see that fraction, but that fractional denominator is not a variable, so there's no need for a quotient rule here. How can I rewrite this in a way where it's gonna feel like an easy power rule problem?
1/3 times the minus.
Yeah, let's split up into individual fractions. And if there's still a fractional value remaining, you can push it out even further as a. So we've got to know how to deal with those fractional denominators and not be really thrown off by it, right? Because this is the same thing as this, but we didn't know how to get to this point so that it feels like an easy. Oh, now you could go through quotient rule, but you're kind of doing more than you have to do. Than to get to your derivative. Okay, so find f prime, set f prime equal to 0. You have difference of squares. And when you factor that x to the fourth minus 1, you get x squared plus 1, x squared minus 1. X squared plus 1 is stuck. We can't factor that anymore. Also, if you set that equal to 0, you'll get an imaginary number. So just the x squared minus 1 that we can keep going with. We can break that down even further, x minus 1, x plus 1. So only two critical points, 1 and -1. And I ran out of room. I didn't write the because statements, but this one will be because f prime is greater than 0, because f prime is less than 0, because f prime changes from positive to negative, because f prime changes from negative to positive. You use this space for 27. We're going to skip 27. Okay, I think we have time for both these here. Let's try 29 and 33. Okay. So if you look at 29, if I want to find the derivative, I got to go through a little bit of what? Chain rule, yeah. Outside derivative. Times inside derivative. Clean everything up, and then you can look in both places, numerator and denominator, for your critical points. Nothing from the numerator. Okay, divide by 3, cube both sides. -3, and for x, cube root of a negative is negative, so positive of negative is negative. Plus 0 in, I'm going to get a positive or a positive, so interval of decrease, interval of increase, but do not include your test numbers. And then there's a relative minimum as well. Okay, last one. 33. We're pretty okay with 29. Okay, so we want to find the derivative here. I do need to get this moved up so I can get it ready for power rule. So let's clean this up. Now, it's a lot easier to find critical points if I can merge this into one fraction. That way I can look at the numerator and denominator a lot more cleanly. So I'm going to find common denominator here. So this is really 2 over 1. So my common denominator can just be x squared. I need to balance my denominator here. This 1 is missing an x squared, so I need to multiply the top by x squared. Then this one has no change, so just a 1. Now it's a lot easier for me to look for my critical points. Now it's all nice and clean under one fraction. Okay, set your numerator equal to 0, set your denominator equal to 0, and place all of those critical points onto your f prime sign line. So you can either leave it as square root of 1 over 2, or you can rationalize it as root 2 over 2. This is around like 0.7. So I'm not going to be picky about whether you rationalize your denominator or not, any of these variations are fine. I'll choose -1 for my test point, 0 and 1. So -1 here, I get 2 minus 1 over 1, that's positive. If I test 0, 0 minus 1 over, oops, sorry, critical point is 0, my bad. So there's another critical point that I forgot to put onto my sign line. So I gotta choose another test point then. I gotta choose -1/2. 1/2. So -1/2 in here, this will give me 2 times 1/4, which 1/2 minus 1, that's negative. 1/2 squared times 2 is also 1/2 minus 1 is also negative. And I could just not even worry about the denominator because the denominator is always positive. It's getting squared. Plug in 1 here, I get a positive. So the graph is going to have a relative max, a relative min, neither at 0, because at 0 there is a vertical asymptote. And I didn't include the because statements, but increase in these two subintervals, decrease in these two subintervals, relative max because f prime changes from positive to negative, relative min because f prime changes from negative to positive. Okay. Next week, we're going to be doing the same process, but with the second derivative. So that's going to give us information about the curvature of the graph, but it's going to feel very much the same. We're going to set f double prime go to 0, find our second derivative sign line, test our intervals, but second derivative is going to give us a little bit different set of information about the graph. Okay, you guys have homework. I'll send out a reminder next Wednesday that I'll be checking homework for 5.3. Okay, all right, forget the phones. Let's do the calendar here. We have a quiz on the 18th and then a test on the 7th. Great. Bottom to it. All right, thank you.
Like, or retake or something.
Oh, yeah.
Like, I think even religion for one. Before school. Can I still?
Yeah, you can still take a retake, yeah.
Because I think, so it doesn't matter, like. Test, right? You don't have to take it for the quiz.
No, I'll still let you.
Yeah. Because I got scared, like I missed the
deadline.
I think the unit 2 came up so.
Yeah, so see if you can plan to take it soon so that you can take more and that you're not trying to do everything all at once at the end of the semester.
Yeah.
So,
Try to take it, but I don't want to get behind in the unit.
that's fair. Yeah, okay.
Yeah, I'll definitely like study some of this.
Yeah, sounds good. Thank you.
I had it when it